What's up, Recalculus? Today we're going to talk about inverse relations and inverse functions. So what we should know from the past, an inverse relation, two relations are inverses of each other if and only if, for each ordered pair x comma y on one of them, the other contains the point y comma x. What's inverse mean? Switch x with y. Alright, so let's take a look at an equation we've graphed here. We have the equation y equals x squared plus 1, a friendly little parabola shifted up 1 unit, and we've got a great little table of values here to go along with some of the ordered pairs. Alright, what we'd like to do here first is complete the table of values for the inverse relation x equals y squared plus 1. So you can clearly see the x and the y have switched, and we are now going to switch the ordered pairs as well. So -2, 5, we switch, and we just keep doing that for every ordered pair in the original chart. So how about you pause the video for a moment and plot those points and see what's cooking here. Okay, I've plotted each of those points from the table from the inverse, and what I do see here is a sideways pointing parabola. Let's answer a few questions about that. Alright, is y equal x squared plus 1 a function? So here's the original function here, and if we apply the vertical line test, I cannot spy anywhere a vertical line that crosses my function more than once, so I will say yes, it is a function because y equals x squared plus 1 passes vertical line test. Let's now ponder whether y equals x squared plus 1 is a one-to-one function. So remember that deals with the horizontal line test. And right here we can clearly see any horizontal line we draw pretty much anywhere will intersect my function more than one time. So unfortunately we say no. Y equals x squared plus 1 fails the horizontal line test. Okay, let's shift up a little bit and then ponder the third part of this. Is the inverse relation x equals y squared plus 1 a function? Well, there's really two ways we can answer that here. The first way, since we have gone through the trouble of sketching the inverse, we can very clearly see the inverse would fail the vertical line test. So we first can establish no, it is not a function. One way to explain that, though, is with the graph of the inverse. And yeah, we can just say x equals y squared plus 1 fails the vertical line test. Well, listen, gang, it's not always going to be convenient for us to draw the inverse and then apply the vertical line test. So perhaps a shorter way, if you're only pondering the graph of the original, is to realize, well, if this guy fails the horizontal line test, its inverse is going to fail the vertical line test. That's always going to happen whenever one fails, the other fails, and they just go in a pair like that. So another explanation could be just to say, well, based on the original graph of y equals x squared plus 1, that graph fails the horizontal line test. And the truth is, when you switch x with y, you switch also the results of the vertical and the horizontal line test. It's just kind of how it works. So let's establish a few little facts about inverse functions down below here. The symbol that represents the inverse of a function is f with a raised superscript of -1. That does indicate inverse function. Inverse functions are reflections of each other over the line y equals x. And to demonstrate what I mean by that, let's go back to our original pairing. If I were to sketch in that line y equals x, what you'll notice As you look at the graph, maybe we could tilt our page a little bit. You'll notice you do see the same image now on either side of that diagonal line. They are reflections over that line. They are mirror images over that line. All right. Not all functions have an inverse that is also a function. We just saw that. A function that passes the horizontal line test is said to be one-to-one, where every x value is matched with exactly one y value, and vice versa. Every y is matched with exactly one x. A function has an inverse if and only it passes the horizontal line test, as we witnessed up above. And one last thing to point out, the domain of f will be the range of the inverse, and the range of f is going to equal the domain of the inverse. When you switch x with y, you switch vertical and horizontal, you switch domains and range. Happy day. Okay, let's use what we just learned to determine if the given function has an inverse, and we will try to justify our answer. Now, I don't know about you, but I'm not looking too forward to graphing each function's inverse, but perhaps we can establish just kind of take advantage of that little feature and ponder the graph of the original function in order to determine what the inverse function would pass or fail. So let's think about number 2 here. We have the absolute value of x minus 2. Now, we don't have to get overly detailed, but if we were just to kind of make a little rough sketch of that function, we know that would be our standard v graph shifted down 2 units. So I don't want to draw the inverse, but I can just look at the original graph and realize, okay, failing horizontal line test. So if I ponder if f of x has an inverse function, I'm going to say no. And that reason, I'll jot down what we just spoke about, because f of x fails the horizontal line test. So I don't need to draw its inverse. I know since my original guy failed HLT, the inverse would fail VLT, and it would not be a function. If I ponder the function in number 3, we could think of this with transformations again. We know that's going to be the cubic graph with a vertical expansion of 2. So it would look roughly something like that. And as I look at that graph, I notice it is going to pass the horizontal line test. So once again, without drawing the inverse of the given function, I already know it will be a function, and that is because f of x passes the horizontal line test. And if we push on to number 4, we do now see a quadratic function, and we're not needing even to go into all the maneuvering of axis of symmetry and vertex. We can just write this in factored form because it happens to be just x minus 3 squared. We can now visualize a standard parabola graph shifted 3 units to the right, and no matter what direction it shifts, oops, off the page a little bit, we know very clearly my parabola fails the horizontal line test. So, will its inverse be a function? Does it have an inverse function? No! And again, that reason is because my function fails horizontal line test. So let's try one more thing, just kind of establishing a few basic facts about different ways we can write the same information, having it mean the same thing but just appear differently. Sometimes viewing information in one form is not going to be ideal. So I'm going to handle the first row for us. Let's imagine we have some function such that f of 2 equals 8. That means the ordered pair 2, 8 will appear on that function's graph. Now in terms of the inverse, everything in these two columns pertains to the inverse. I know the inverse simply means switch x with y, and that can easily give me 8, 2. And to write the inverse notation from that, I would then be able to say f inverse of 8 equals 2. So all 4 of these pieces of information state the same pairing of 8 and 2. They just state them in alternative ways. Could you try the next 3 lines yourselves and pause the video, check back with you in a moment. Okay, welcome back. Let me just get this map out of the way, and hopefully as you compare each box of information to what mine is, you have successfully managed to rearrange, oh, there's the bell, rearrange every pairing to say the same thing in a different style. Well, that's it. The bell has rung. Peace out, Cub Scouts. Ta-ta.